Okay, the next speaker is Professor Feng. His talk is identification of a linear latent hierarchical structure. Professor Feng is currently an associate professor in the Department of Applied Statistics at Beijing Technology and Business University. Before joining BTBU, he received a PhD in the School of Computer Science and at Guangdong University of Technology from 2017 to 2020. Then he did postdoctoral research in the Department of Probability and Statistics at Peking University from 2020 to 2022. From 2019 to 2020, he was a visiting PhD student in the Department of Philosophy, CMU. So now let's welcome Professor Feng.
Okay, thanks. I'm there on my screen. Okay, thank you very much, Professor Jin Zhujia, for your very kind introduction. Hello, everyone. I'm Feng Xie. I would like to begin my talk by thanking for the organizers for inviting me. My topic today is the identification of linear latent hierarchical structure. This work was published in ICML 2022. This is joint work with B Wei from Carnegie Mellon University, Zhen Mingchen from Guangdong University of Technology, Yang Bohe from Peking University, Zhigen from Beijing Technology and Business University, and Kun Zhang from CMU. This topic is focused on the causal discovery, which means that learn the causal structure from the observational data. As we know, the latent variable models are ubiquitous in social science, economics, and psychology, and so on. Especially in some real-world scenarios, the observed variables, such as words and image pictures, may not necessarily be the underlying causal variables. Besides, the variables of interest are usually hard to measure or observe, such as the strength coping model. Here, the strength, depression, and coping are hard usually to measure. So the open problem is that how do we learn the underlying latent structure only from a few observed variables? At present, roughly speaking, there are two classical strategies to address the above issue. One is the measurement-based model. It's assumed that latent variables have direct measured variables at children, such as figure A. Another one is the latent tree model. It assumes that each latent variable has at least 3 neighbors, such as figure B. Compared to the measurement-based model, the latent tree models allow some latent variables have only latent nodes at children, such as I1 over here. Even though the latent tree model can be seen as a latent hierarchical structure, the latent tree model usually assume that there is only one path between every pair of variables in the system. So let's consider the figure C. We can verify that both of them cannot recover this graph. So in this topic, we want to focus on the more general scenarios. In this work, we restrict our attention to a particular type of linear causal model. Here we donate the X, the observed variables. L donate the set of latent variables. Compared to the existing models, our model is more general scenarios, where some latent variables may have only latent variable at children, and there's no restriction on the number of paths between every pair of variables. However, it is impossible to identify the latent structures without any further assumptions. So the key question is that can we find some sufficient conditions that render the causal structure of a latent hierarchical model of interest identifiable? Okay. To address the above questions, we here introduce the two important conditions. The first one is the non-Gaussianity. It says that all noise terms or variables follow non-Gaussian distributions. This condition is very useful to identify causal directions between any two variables. Okay, the next condition is the structural condition we defined is minimal latent hierarchical structure. It says that each latent variable has at least 3 neighbors, and its latent variable has at least 2 pure children. Condition 2 ensures that the structures among latent variables does not include any redundant latent nodes, such as the figure B. This is a counterexample of the minimal latent hierarchical structures. L6 and 7 may be a redundant latent nodes. Compared to the latent tree models, here we do not allow the only one path between every pair of nodes in the system. Okay, before describing the identification algorithm, I will first introduce the gene conditions. It is a tool for testing D-separation in latent variable models. Gene conditions say that for a pair of vectors D, Y, it's ordered pair vectors D, Y follow the gene conditions if and only if there exists a non-zero omega, such as X omega transport time Y is statically independent from Z. Graphically speaking, if we test the ZY follow the gene condition, we found the ZY follow the gene condition. We can say that there is a ignorant subset of the common cause of Y to be separated from Y from Z. For instance, consider the graph. Let Y equal to x1, x2, x3. Z is x4, x2, x6. We found that ZY follow gene conditions. Then there exists a exhaustive subset of the common cause of Y, that is x1, x2, x3. Or here is the job challenge to separate x1, x2, x3 from x4, x7, x6. Next, I will show that we can estimate the latent hierarchical structure by checking some gene conditions. So our method consists of 2 steps. It first locates all latent variables. In this step, it consists of 3 small steps. It first identify causal clusters from the active variable set. Then we determine the number of new latent variables that need to be introduced for these clusters. Next, we update the active variable set. Then we recursively run the 3 steps to locate all latent variables of the system. The next step, step 2, is infer the causal structure among the identified latent variables. It contains the first we identify the causal order among latent variables. Then we remove the redundant edges between latent variables. We want to emphasize that we have no idea about the number of latent variables and the level of the structure because it is the latent hierarchical structure. Okay. Next, I will give an example to illustrate our method. The upper left graph is the ground truth we want to recover. We first put all observables into the active set. Here, active set is it means we use the observed in this iteration. Here, solid blue nodes indicate the active variables. Step one consists of three phases. The first one is we want to find the global clusters. Global cluster means that if the variables in this group share the same set of latent variables, then we can find that there exists a latent variables. For example, if we test y equal to x1, x2, we find that x1, x2 follow the gene conditions with the remaining other variables. It implies that x1, x2 is a global cluster, which means that the x1, x2 share a latent variables in the system. In these procedures, we test the gene conditions, and we can find 8 clusters over here. Then we need to determine the number of latent variables that need to introduce for these clusters by using these 3 rules of the proposition 2. The three rules provide the conditions under which the clusters of variables share the common latent parent and should be merged. This is because the structure of interest is a hierarchical structure, and we don't know the level of the structure. So here, without going to the detail, I just give the introduction about them. Roughly speaking, the 3 rules say that the current 2 clusters are treated as a whole clusters, and to test the gene conditions with the remaining variables. And if it satisfies the gene conditions, when we merge them, it implies that the 2 clusters share the same latent variables. Okay, using these 3 rules, we can determine the number of latent variables in current interaction. Now we update the active set to find the remaining latent variables. Here, I want to let me arise the following concerns for hierarchical structures. How can we further find latent variables that are the parents of latent variables, and how can we check the gene conditions or the latent variables without observing them? It means that we do not recover distributions of latent variable of interest. We just use the measurement variables to recover and test the gene conditions. Okay, the answer is yes, we can. Yes, we can. And the main point is that the linearity assumption and the transitivity of the linear causal relations. So we can use their observational descendants to test the gene conditions. Proposition 3 says that if we want to test the gene conditions, including some latent variables, we can use the corresponding descendants to test the gene conditions. For instance, if we want to test the L4 x14 share the latent variables, we can test the x4 x1 x4, and instead of the x1 instead of the L4, and we find using this strategies, we can continue to testing the gene conditions and recursively find the remaining latent variables. Okay. Finally, we iteratively run the above three procedures until our latent variable or system are discovered. Let's continue to see the procedure. First, we continue to find the global clusters. Here, there are 3 clusters. Then we determine latent variables by proposition 2. Okay, we found, okay, there are 3 latent variables, L1, L2, and L4. Then we updating the active set and continue to find the global clusters. Over here, we found that L4 and L5 is a cluster, and L6 and L8 is a clusters. Then we determine the latent variables. Here, I want to emphasize that we do not introduce the new latent variables for these 2 clusters. This is because L1, the latent variable L1 has been introduced in the previous iterations. Okay, it means that we need to stop and imply that, we found that the latent variable of the system, all of the latent variable of the system in the system. Then we in the step 1, we found all latent variables. In next 2, we further need to infer the core structure among the identified latent variables, because even though we have know the number of latent variables, but we don't know the structures, especially the core direction between them. Okay, I will show 2 simple example. Here let's continue to consider the figure. To infer the causal direction between L2 and L5, we need to test 2 conditions. The first one is L2, L7, and L2, L4 over here, L4 and L6. We found that it follows the gene conditions. While we exchange the L4 and L2, we found that it violates the gene conditions. By two conditions implies that L2 is cause L4, L2 cause L4. Okay, we found the core directions between L2 and L4. Similarly, we do the same procedure. We test the L4, L3, L7, and L3, 8, 6. We found that it follows the gene conditions. While we exchange the L3 and 8, we found that L8, L7, L3, L8, and L6 violates the gene conditions. The results imply that L3 caused L8. Okay. It means that we found the core direction between L3 and L8. Finally, the unknown latent core structures is fully reconstructed as given in the right graph. We found that the structures estimated by our method is consist of the ground truth graph. Okay, I summarize the identification results. It is important in causal inference. The identification says that suppose the input data follow the linear causal model, and under the assumptions of non-Gaussian and the minimal latent hierarchical structure, then the underlying causal graph is fully identified. by our proposed method, including the latent variables and their correlationships. Note that if you input the data, if the underlying core graph is only a tree-based graph, then the output graph by our method can recover with only step one. We don't need to go further to step two. We just use the only step one. We can recover the latent tree-based graph. Okay. To evaluate our method, we first apply our method to some simulation, some significant data. We here consider 4 cases, including the measurement-based case 1 and 2, and tree-based case 3, and latent hierarchical structure case 4. The question is, can we recover these 3 cases, including the core directions? Here we make comparisons with 5 methods. The results given in the table 1. We use 3 metrics to evaluate. The first one is the structure recover error rate. It says that measure the falsely recover the graph. The second one is the error in hidden variables. It measures the omitted latent variables. And the last one is the correct ordering rate. It measures the corrections of the core directions. Okay, as you can see on the table 1, we found that our method outperforms the other variables with all 3 evaluation. The first structure recovery error rate, and the second is error hidden variables over here, and the last one is the correct ordering rate over here. Note that the 3 compared method, FFC, BPC, and CRRG and CRNG cannot infer the core directions of the variables, so we do not output the results. Okay. We also apply our algorithm to multitasking behavior model. This is this is a hierarchical structure model. This data consists of 22 samples. It includes in details. It includes 4 latent factors. The first one is the multitasking behavior. The first one is multitasking behavior, MB here, and the last 3 is the speed, error, and question. And each of them may have some measured children. Speed have 4 children, and error have 4 children, and the questions have 4 children. And the multitasking behavior factors have 3 children, but these children are hidden. It means that we cannot directly measure. The question is, can we use can we recover the structure? So we here still comparisons with the above 5 methods. We found that our methods over here cover the consistent with the hypothesis model given the HIM 29, and we found that the other method cannot recover the whole structures. Interestingly, we found that the latent tree-based models such as CRNG can find the multitasking behavior latent factor here, but they cannot find the S2, S3, and S1 is share the latent variables is the speed. Okay, and the other things we found that they cannot inference the correl direction between them. It's just because they just use the latent tree models. Okay, and these are in summary, these results against the indicate that our method has better performance than other algorithms in learning latent hierarchical structures. Okay. Finally, I will briefly summarize the main conclusion. The first one is it is initial to learn linear latent hierarchical structure. In fact, it's initial to learn latent hierarchical structure. The second is we here provide sufficient conditions for structural identifiability. In the future, we will extend our models, our work to unfactored models or nonlinear hypothesis structures and so on. We are eager to propose a non-parametric method algorithm to handle the latent hierarchical structures. Okay, that's all.
Okay, thank you, Professor Feng. So do you have any questions from the audience? I have a quick question. I see in your example, all of the observations, there is no any direct arrows from any variable to another. So is this example a special case, or you just consider this kind of structures?
Okay, I see. Good questions. In this paper, we assume that the variables have no direct edges between them, but in our future work, we are working on it.
Okay, thank you.
Okay, thank you.